Hi, my name is Corbin Weiss. I'm a freshman math pre-med major.
My name is Caleb Mons. I'm a sophomore biophysics major.
My name is Jonathan Castro. I'm a senior music pre-med major. In this experiment, we'll be investigating the relationship between potential energy, electric field, and magnetic field. Specifically, having a solenoid current create a magnetic field, which will then create a current in a ring, which will then have a magnetic field opposed to the original magnetic field.
We got power coming from the wall through this transformer, which goes from 0 to 140 volts. Then we wired it up to a switch. Then the power goes here to power our solenoid. And so when we flip the switch, it will induce a magnetic field in the solenoid and launch the ring. And then our ruler here is for reference to see how high it goes. We can use that to calculate the energy using good old MGH. So.
All right. 3, 2, 1.
Nice.
In this lab, we focus on 3 concepts: Faraday's law, Lenz's law, and conservation of energy. To help explain how they all relate, I'll draw a diagram of our system. We have our iron core, our solenoid, and our aluminum ring that sits on top of it. In our experiment, we see that this aluminum ring gets shot upward, which implies that there's some transfer of energy. At its minimum height, we know that all the energy is kinetic. And at its max height, we know that all that kinetic energy has become potential energy. But what causes that change in height? It's the impulse. But where does the impulse come from? Well, there's an electric field in our solenoid, and that creates a magnetic force that induces a current in our ring. And that induced current creates an impulse that shoots the ring upward. And we can represent impulse by force times the change in time, and in our case, magnetic force. But how does that relate to energy? Well, energy is equal to the integral of force times the change in distance, and that force is still magnetic force. But we don't see time yet. So if we want to include time, we can write our equation like this. And we know that dx over dt, change in distance over change in time, is equal to the velocity. And here's our relationship. But we still don't have a relationship between energy and voltage. So let's go a few steps even further and say energy equals the power times time. And we know that power is equal to voltage times the current times time. And here we do see
Mm-hmm.
Let's try it.
oh yes, this is much better. Almost 150.
Oh no.
So that's all the trials we need.
Yeah.
1, 2,
Okay, yeah.
Ready?
Yep.
1, 2, 3.
Alrighty, so here's the data we got from our experiment. We used 5 volts up to 50 volts to see how the energy of the launched ring related to voltage. So the way we did it is Caleb recorded like 3 trials on his iPhone, and we found the maximum height. Subtracted that maximum height from the initial height on the ruler that the ring had, and from that we used mass times gravity times height to get the total energy, and then averaged those energies for the 3 trials, like that one right there. So then plotting the voltage versus the energy, we found a pretty significant relationship, linear relationship between voltage and energy. Our R squared is 0.9969, so our data looks pretty good. Most of modern technology relies on Faraday's law. Wireless charging, maglev trains, transformers, and generators. Generators are probably the most important thing in our lives right now, as we rely on alternating current for most of our existence. Generators work very similarly to our experiment by exposing a coil to a changing magnetic field. And in the case of a generator, this produces a current in that coil, which is then used for an alternating current source to drive our lights and our heaters and our laptops and definitely everything you are using to watch this video. So Faraday's law is very important for everything we do today.
Okay, so did you see that?
Ooh! Wow.
Ooh!
Yeah, do 20.
No, just
Oh yeah, okay. We have power.
What? Let's try 110 again.
Yeah, do like,
Yeah. Fire the hole.
I mean that was pretty good, but
let's go out a railgun now. That's like,
Oh, that was awesome.
is this what you would call it?
what?
Is this what you would call it?